Welcome to the class, Tatu. There you go. I can see your microphone.
Good afternoon, sir.
Afternoon. Before we start, I just want to make sure that we're heading in the right direction. I think you're writing 2 tests this term.
Yes, sir.
One is, I'm pretty sure, but I can be wrong. One of the tests is going to be on electrostatics and magnetism, and also circuits.
Yes, sir.
So electrical circuits. And the second test is a chemistry test. And that's going to be on, I think, chemical change. Now, it's important that you exactly know which test we're going to write first and which one we're going to do second. Can you actually choose which one you want to do first and which one you want to do second? Or not?
No, sir. We cannot.
Do you know which one is first?
I'm guessing it's the electrostatics one because that's usually in paper 1, right?
Yeah.
And you gotta write them in order.
Okay. So we just need to make sure of this, because we are on track of, we finished the electrostatics, so we're going to go to electrical circuits and magnetism and stuff. So it doesn't help us doing all of this now, and then you're writing your chemistry test first. You understand what I'm saying?
Yes, sir.
Because then we're not going to have enough time to actually get through the chemistry. So somehow other way, you just need to make sure that we are on the right. I'm not keeping track of what you need to do. I'm just helping you. I'm just a person that is actually helping you to understand the work. And then I also heard that the physics exam was quite difficult.
Yes, sir, it was.
Did you do well?
Yes, sir. The exam?
Yeah. No.
Not necessarily. I passed, but it wasn't.
Okay. Because I know of students that normally get 80 and they got like 50s. So I'm assuming it was difficult.
Yes,
Okay.
it was.
If you want to work through that paper at some other stage, we can also do that.
Yes, sir.
But then you have to send me the paper. I can't
Yes, sir.
remember.
I'll ask.
I can't remember if someone has sent me the paper already.
It should be Auntie T because I asked her to the last time we spoke about it.
She sent me the paper.
Yes, sir.
Really?
Yes, sir.
Maybe on email. Maybe on email.
Yes.
Just want to make 100% sure I've got it. Because I get a lot of correspondence. I can lose something. No, I don't have it.
I'll send
Oh, no, I've got it. I've got something here. I'm not sure what it is. I think it's a paper, yeah. So want to just check. It's something with your marks on it.
Yes, sir.
So I'm just have to actually work through this. This is also your mark. I don't see any paper yet. No, it's only marks.
That's the only thing I got too.
Pardon?
That's the only thing I got too.
Oh, I got it here. I got it here. I didn't look any further. This is math and science then.
Yes, sir.
Okay, what I need to do, we need to, if you want to, you need to work through, but I don't have the question paper. I only have the
answer sheet.
I only have your answer sheet. It's very difficult if I don't have the questions. So you want to make 100% sure I don't have the questions? I only have answer sheets. You need to send me the paper as well, the question paper.
I can send them to you right now. if I could have your email address.
Yeah. Okay. I'll send you. You don't have to send it now. You can send it after the lesson as well.
Oh, okay, sir.
Okay. I sent you my mail. Okay. What are we doing today? We
Sir,
finished electrostatics, eh?
yes, sir. But I was struggling on magnetism, and I just started electric circuits yesterday.
Good. So what do you want to do today?
Magnetism, sir.
Okay, but you must show me the examples you're struggling with, because I'm not sure what part of the magnetism you've done. Have you done Faraday's law and
That's
Lenz's
the one
law?
that's the one I'm struggling with, sir.
Faraday's law
Yes, sir.
of electromagnetic induction.
Yes, sir.
Okay, let me start a new one. Okay, this is going to be difficult to explain to you. Just going to get a piece of paper ready or a sheet ready with stuff on it.
Yes, sir.
So you struggle to find that which direction the spool is running,
Sir?
which direction that thing is running, or just give me a second so I can just get Faraday's law here. Have you done the motor and dynamo rule?
No.
You haven't done that.
Yes, sir.
Just always remember just to send me in the morning what you're going to do. It just makes it, if I find some time, then I can actually just get stuff ready for you.
Yes, sir.
It just saves us a little bit of time. This is the wrong page. Why have I done the wrong page? Okay, let me start by copying and pasting this. Okay, so you've done the right hand rule.
Yes, I have.
Right. Okay. So let's assume, we're going to work with this middle diagram first. Let's assume I have an electrical wire there. It's that blue
Yes,
thing.
sir.
Now,
Yes, sir.
if I can find out in which direction the current flows, we're going to ignore the electrons for now. If I can figure out in which direction the current flows, I can actually find the direction of the magnetic field. So that's called the right-hand rule.
Yes, sir.
You use your right hand and you form a fist with your thumb pointing up or in the natural direction. So if the current is moving upwards in that wire and you put your fist around it and your thumb will point in the direction of the current or the flow of the current. And the way that your fingers is actually bending around the electrical current will give you the direction of the magnetic field. You understand that? Can you see that?
Yes, sir.
Okay,
Yes.
those red arrows gives you the indication of what direction the magnetic field is. So there's two other ways of just showing you what to do or just indicating what is happening. Now, if I look at this blue section here, do you know what a dartboard is? A dart.
A what?
If you throw a dart towards you, it looks like that blue section there. So that point
Oh,
of the
yes, sir.
dart is coming towards you. So the dart is flying in direction of the current. So if you take your fist now and you point your thumb towards your eye, the thumb is the point or the front end of the arrow. If that comes towards you, then your fingers will clench around the dart like that, or around the wire like that. So your magnetic field will be in anti-clockwise direction. Do you understand that?
Yes. Yes, sir.
In the next drawing, I have a little cross. Now that cross is like the back of the dart. A dart's got a feather or a cross at the back that helps stabilize it. So that cross indicates that the wire with the electrical current is flowing in towards the whiteboard. So that it's flowing, it's moving away from you. If it's moving away from you, you point your thumb into the computer screen, and if you clench your fingers around that, that will show you which direction the magnetic field is like. Now, if you don't know this, you will lose 1 mark in the exam. And the mark is very difficult to lose because you always have a 50-50 chance of guessing it right. It can only flow clockwise or anti-clockwise. It can't
Yes, sir.
move any. So this is not a big issue, not a really big issue. We're going to move towards the equation and to work out sums, but this is not a difficult part of your syllabus. Lenz's law is more difficult. Okay, so you understand this. So
Yes,
let's
sir.
look at this electrical current or circuit at the right, on the right-hand side. Now, the long bar is the positive side of the magnet, not the
Yes,
magnet,
sir.
the battery, and the negative side is that smaller side.
Yes, sir.
So your electrons will move from the negative side of the battery towards the positive side. Why? Because the negative side repels negative electrons, negatively charged electrons, and they will move in that direction.
Yes, sir.
So that's electron movement is from the negative side of the battery to the positive side. Well, conventional current is from the positive side or in the opposite direction
To the
of,
negative side.
yeah. So if I'm just going to highlight that area. So there's the battery and there's the electrical wire coming out from the battery. So in other words, my current will flow in this direction. If I take my thumb and point it in that direction and clench my fingers over the wire, you'll find that the electrical field will be in that direction. Agreed?
Yes, sir.
Okay, so you know how to do that. Good. That's the first step. Right, so they might, in a short question, give you the following diagram. So all of the work we're doing at the moment, you can do. You understand this, and you've looked at it.
Yes, sir.
Good. So I'm just going to paste a small drawing. So they have this drawing and you must complete the drawing. Okay, in other words, the current is flowing in that direction. So I'm putting my thumb in that direction and I'm clenching my fingers over that wire. So my electrical field will be in that direction. Agreed?
Yes, sir.
So it will come out of the inside of the current and it will go into the whiteboard at the back or over it. So it moves in that direction. It will come out here. So we'll have dots there. And it will go in there. So you'll have crosses there. You'll be able to do that.
I guess so.
Yeah. But like I said, it's difficult to move marks here because, okay, let's just do it again. I'm going to put my thumb in the direction of these arrows. And I'm
Yes,
going to
sir.
clench my finger over the wire. Over the wire means it goes in on this side. So if the arrow or the dart goes into the board on top, you'll see a arrow, a cross at the back of the arrow. Do you agree?
Yes, sir.
If it comes out at the bottom, the point of the arrow will move towards your eye and you'll only see the front of the arrow, the point. And that's why it's dots there. Okay. So those are just like small multiple questions or just 1 mark questions they might ask. It's not even a given that they'll ask it. Okay, let's look at Faraday's law of electromagnetic induction. There's your equations. Have you seen these?
I've only seen 2 of them, sir.
You've probably seen the first one.
Yes, sir.
Okay. Right, now this is a lot of drawings. Okay, I'm just going to explain. So the EMF generated equals minus N times the change in magnetic flux divided
sir.
by the time. Now, magnetic flux. Okay, let's just look at that. Magnetic flux is B times A. or change. So the change in magnetic flux is a change of B times A. Now, B is the strength of the magnetic field, force
Yes, sir.
of the magnetic field. And that is in Tesla.
Oh, okay, sir.
So T. And A is just the area of your loop. So if you have a circle, it's pi radius square. If you have a square, it's length times breadth. Area of the loop. Do you call it a loop?
No, sir.
What do you call it?
Area of base.
Of ACE.
Base.
Base. Well, look, it's not a base. It's basically basically a copper wire that's either in the form of a circle or the form of a square or something.
Oh, okay, sir.
Have you actually opened a small electrical motor and see there's a lot of copper wiring in it?
No, sir.
Okay. So I'm going to explain that. I'll explain this to you in a minute. So an N is the amount of loops. And T is just time in seconds. T
Yes, sir.
is time in seconds. So electromagnetic induction basically works on the following principle. If I take a copper wire, there's my copper wire. I'm just going to try and draw a better one. I take a copper wire and I bend it in the form of a loop, like a circle or something. If I place this between two magnets, there's the one magnet. Let's assume this is the north side of the magnet, and this is my other magnet, south side of the magnet. Doesn't matter. It can be north on top, south at the bottom, doesn't matter. If I start spinning that thing, so if I take a copper wire and I spin it between two magnets, it will generate electrical current. This is how a dynamo works. Do you know what a dynamo is?
No, sir.
A dynamo is a contraption like that. It's a copper wire or conductor that's turned between two magnets. If you have an old bicycle light, it works on a dynamo. So you've heard of hydroelectrical. You've heard of hydroelectrical plant. No.
No.
Okay. So what they do is they take a dam wall, or take a dam. There's a dam wall, and then there's a lot
Yes.
of water on the side, and then they allow the water to run through a gap in the wall, and
Yes,
inside
sir.
that gap, they've got a dynamo. It's a it's a it's a big thing. It looks like a fan. So the water runs over that fan and spins this very fast. But that thing is full of copper wire and in a magnet. So what happens is the water pushes that fan with a lot of force. So it can turn a huge heavy fan with a lot of copper wire. And once that copper wire starts turning or spinning inside a magnet, then we have electrical current. So in Lesotho, they have a huge electrical plant that generates electricity.
Yes, sir.
And this is what Faraday's law is based on. You take a copper wire, you spin it inside a magnetic field, and then you generate electricity. So if you have a coal, the way coal works, you burn coal, it makes a lot of heat. So there's my plant that burns coal. It makes a lot of heat, and that steam is run over a big fan inside with a conductor like copper wire inside a magnetic field, and that generates electricity. So this is a way we generate electricity through Faraday's law. Okay, but anyway, let's get back at that. The first thing we need to know is how to change magnetic, or how to determine magnetic flux or flux. So if I have a copper wire, let's say there's my copper wire, I've bent it in the form of a rectangle. Then A is just the area of this loop. If this is 20 centimeters and this is, let's say, 30 centimeters, then the area is going to be in what? In meters. So it's 0,
Right.
2 times 0, 3, and that's 0,06 meters square. So that's the area of the loop, and that we're going to fill into A's value. Now, this is placed inside a magnetic field. So we have a magnet here and a magnet there. And B is the strength of that magnet in Tesla. So that way you can determine flux, magnetic flux. Now, the more obviously, I mean, at this stage, we only have like one copper wire, but you can have hundreds of these copper wires. You can take this copper wire and just take hundreds of them and turn it into that around that same form. And then you have hundreds of ends, and then you can generate more electricity. So the sums aren't difficult. It's just basically the filling in of values, right? So you're going to not even have to learn that. You're going to be given that. All you need to know that that flux is determined by the area of the loop times the,
Strength.
But there's a small problem. We're assuming that we're turning this thing 180 degrees the whole time. You can also just turn it 30 or 20 or 50 degrees. So you can just make a quick turn on that big loop and it will generate electricity. That's why this formula is basically a bit, it's not good on its own. You need to actually adjust that formula for an angle that you turn it on. So we just do delta BA as follows. The change in the magnetic strength times the area can be calculated by doing B if A cos theta minus B initial A cos theta. Now I can actually have various angles there. I only have to turn that big loop 30 degrees, and then I can work out the change in flux. So the area of the loop will stay constant. You're not changing that. And the magnetic field should stay constant. So it's just the change in that angle that determines the flux in that loop. Okay, now, very important. This angle can be a huge problem. I'm going to show you a couple of drawings. I'm going to start off with this one. Very difficult to see this because it's supposed to be three-dimensional. Those blue lines represents the magnetic field. So the direction of the magnetic field is from left to right. Now I have a coil here. Can you see that gray? That's a coil. So it's just a bunch of copper wire that we've actually made a coil of. Now, there's an angle that we call the normal. And that is if you take one coil and I just take a pen or something and I put it right through the center of this. So I'm just going to redraw this. It looks slightly weird. I'm going to take this coil and put it down on its side. Now, the normal is just a line that goes through the middle of that coil, and that's also perpendicular onto the surface of that coil. You see that? Imagine you've got a circle. Imagine you've got like a ring in front of you. You're putting it down on the table, face down. And now you're taking like a pencil and you're putting it in the middle. So the angle between the pencil and the flat part of that coil is 90 degrees. So if this is my normal, I'm going to put it in there. If the angle between the normal and the magnetic field is 90 degrees, then there will be no flux. Right. So students do the following. They imagine that these magnetic fields are like a shower. Imagine standing underneath the shower and you have a bucket in your hand. So I'm going to just do this. This is the water coming from my shower on top of my head. Now I have a bucket. Now the bucket represents that coil. There's the bucket. So if I put the bucket this way. So when my normal and the magnetic field are perpendicular to one another, can you see that?
Yes, sir.
Then I will catch no water in that bucket. So there will be no flux. No flux means no electricity. If I tilt it, so there's the normal now. Now the angle between the normal and the magnetic field is, say, for instance, 45 degrees. Then there will be flux. There will be current. If I take my bucket, in other words, my bucket has now been, I've taken the bucket and I've basically put it like this. So the angle between the normal and the water is 45 degrees, and then there's some water will actually be accumulating in the bucket. Do you agree?
Yes, sir.
But I get the maximum magnetic flux if there's no angle between my normal and the magnetic field. So now my bucket or my coil is like that. And now I'll get maximum flux. Right. So I can work out what is the EMF produced if I just have the change in angle from position, say, from A to position B. If I can calculate the change of angle,
Yes,
and
sir.
if I have the magnetic field strength, and if I have the time it took to make that change, it can be a hundredth of a second. In a 1/100th of a second, I change the angle from 45 to 0. So flux is produced. And if flux is produced according to the equation, then I'll also have EMF. So we can work out the following. Let's say that I have a magnetic field there. And the A value or the B value is 0.03 Tesla. That's the strength of that magnetic field. I have a coil, and the area of the coil is, let's say, 0.4 meters square. So that's that coil. There's the coil. I'm going to change the coil from 0 to, let's say, 30 degrees change in angle. So that's the way I'm going to turn it in 0.01 second. All right. And there's only one coil. I want to know what the EMF is. So E equals minus N, change in flux over time. That's your main equation. Now, I'm changing that angle. So I'm going to work out the change in flux first. The change in flux is the B times the A value initial. B will be initial. Doesn't matter which one. The final minus the initial.
Yes, sir.
Cos theta minus B initial A cos theta. So B is 0.03. A stays the same. So a lot of students just do the following. B doesn't change, A doesn't change. So I just have BA. I'm factorizing them out. They stay the same. And the only thing that changes is the angle. So the final angle is 30 degrees minus the initial angle, which is 0 degrees. So the change in flux is B 0.03 times the area of that coil, 0.4. And now I've cos 30 minus cos 0 degrees. Okay, that I'm just going to type in my calculator.
Sir,
So I'm struggling to find my calculator. It's like running around.
I'm getting 0.01.
Okay. 0.01.
Yes.
What? Weber.
Yes, Weber.
Weber. Right. So I prefer working out this separately. You don't have to. You can all put it into that big equation. But now I can actually work like this. Minus, well, how many coils do we have? 1. The change in
Yes, sir.
is 0.01. And the time was, oh, okay, well, this is dumb. It's 0.01 second. I'm going to change these seconds to 0.02 seconds. So otherwise, we have all the values looking exactly the same. 0.02 seconds. Right. I have a negative value. It doesn't matter. I'll explain to you a bit later why it doesn't matter. 0.01 divided by 0.02. And that is 0.5 volts.
Yes. Isn't it negative, sir?
Yeah. Okay. Negative. This is called alternating current. You get DC and AC current. Now with these generators, you actually produce AC current. Now AC current looks like this sine curve here. Up, down, up, down. So the top part is like positive and the bottom part is negative. So it doesn't matter. You'll get positive, you'll get 0.5 volts positive and negative.
So, sir, even if I write it without the negative, I'm still going to be correct.
I'm not 100% sure how they want the marking to be done. You can just look maybe in your textbook at how they write the final answer.
Yes, sir.
I would assume they just want an E value. Therefore, E equals 0.5 volts. That negative is just, they just put it in there. Basically, if you get a negative value, because if we've changed it from 30 degrees to 0 degrees, we would have a negative answer. And then that negative just fixes the answers to a positive. I don't even know why they put a negative there. It's like unnecessary. So this is a
Yes, sir.
basic calculation. Okay, let's see what you have to know. Okay, this is quite important. This is a lot of theory, this chapter. Okay, it's a lot of theory. These calculations are not that popular. It's more theory. So I'm going to show you in the next question, I'm going to show you a graph.
Yes,
This
sir.
is quite important. I don't like this chapter at all. You haven't done Lenz's law yet.
No.
Okay. Okay. This is now in Afrikaans, but it doesn't matter. It's just a graph. This graph shows you, okay, so this is a graph of change of flux, magnetic flux. Okay, let's look at this. Now, look at what happens at A. At A, I need to paste another graph here, otherwise you're not going to understand it. Let me just put another graph here. This is quite important. This can be very difficult if you have to try and figure this out. It's going to be a nightmare. So I'll have to show you this. I'm just going to show you these two graphs. Can I make it small like this where you actually be able to see? If I make
Yes, sir.
Okay, look at these two graphs. So this is a graph of the change in flux and EMF. So look at A, B, C, D, and E. They are various different positions of where that loop can be in the magnetic field. Now, those arrows are the magnetic field. And at A, the angle between the normal and the magnetic field is 90 degrees. Can you see that?
Yes, sir.
So we have no flux. Flux, you can visualize that as catching the water. You can't catch any water, there's no flux. So at A, the flux is 0. But
Yes,
at
sir.
A, we have a maximum EMK. Or let's say the change in flux is 0. And that gives me
Yes, sir.
maximum EMK. All right.
Yes, sir.
This is actually for you, EMF. All right. At B, there's a 0-degree angle between the magnetic field and the normal. At that state, at B, we are actually catching the maximum amount of flux. Why? Because we are accumulating the maximum amount of
Sir,
field.
can I please ask?
Pardon?
Isn't B like, okay, if you had to make B a bucket, since like it's facing towards the
Water.
east direction, right? So
Yeah.
shouldn't you be catching anything? Because if you look at the one at D, it's facing the opposite direction in which the
Oh, yeah.
the thing.
Sorry, that's just the arrow of the angle. It can be, the arrow could have been in this direction as well. Doesn't matter.
Oh yes, sir.
So it's an open bucket. The bucket doesn't have a bottom really. It's just a ring.
Oh
It's just a
yes, sir.
ring. So you're catching all the water. So that's why your magnetic flux is maximum. But your EMF is 0 or minimum. And so that thing spins around in that magnetic field between maximum 0, maximum 0, maximum 0. So these two graphs are kind of very important. So
Hmm.
I'm just gonna, you can take a screenshot of that if you want to.
Yes,
They
yes,
can
sir.
actually ask you to fill in these graphs or draw these graphs.
Let me just take the screenshot quick. Where is it? Oh yeah, here is it. Yes, done.
All right, good. So they explain it in this way. E is negative N, change in magnetic flux over time. Now, change in magnetic flux is basically what? Your gradient.
Yes, sir.
So when the gradient is 0, then I have what? If this gradient, that thing is a gradient. If that gradient is 0, I will have no E value.
Oh yes, sir.
Sorry, I'll have a maximum E value. I'll have no flux. So look at this red graph. I'm going to show you where the gradient is 0. There, and there I have no gradient. There I have a negative gradient, positive gradient, positive gradient. But at A, C, and E, I basically have no gradient. If I have no gradient, no,
Yes, sir. If you have like
if I have
no
no
gradient,
gradient, I'll have no flux.
yes, sir.
Okay, just look at this. I'm not sure if you even have this in your book.
The graphs.
Yeah,
No, I do not have them, so.
then you probably won't be examined on them. Okay, so let's just play around with 1 or 2 examples. And paste you. There's just, they give you this drawing, and then they say a rectangular loop is placed in magnetic field. Oops. In a magnetic field of 1,5 Tesla. The length equals 0,6 meters. The width equals 0,2 meters. Okay. I want to know, one, what is, let's say, the magnetic flux at A? That's a possible question. And number 2, what is the EMF produced in 0,02 seconds. Right. Okay, well, the first question is just a basic one. What is the magnetic flux at A? Well, we're going to say flux equals BA cos theta.
Yes, sir.
Right, let's see what's happening here. B is 1,5 Tesla.
Yes, sir.
A is the area, so it's 0,6 times 0,2 now.
Yes, sir.
And cos, what is the angle between the normal and the magnetic field?
It's 90 degrees.
It's not. It is 0 degrees.
You said at A, right?
Yes, at A. Sorry, this is A.
But isn't the thing perpendicular, therefore it should make a 90 degrees?
Yeah, well, wait. This is the normal, this red one. Do you agree?
Yes, sir.
But the angle between the magnetic field arrows and the normal is 0 degrees.
Oh, yeah. Oh, yes, sir. Yes, sir.
I'm going to show you what it would look like if it were 90 degrees. Those are arrows are my magnetic field. If it was 90 degrees, then that loop would have lied like that. And so that would be the normal.
Oh, yes, sir.
So at the moment, it's in the same direction. Let's go back to that. We finish this and then we go back to the slide, 0 degrees. And then you just put this in your calculator. So it's 1.5 times 0.6 times
0,18, sir. Weber. 0,18 Weber.
Very good. 0,18 Weber. Bang. Okay, good. And then the EMF produced in 0,2 seconds, 0,02 seconds, E equals minus N, change in Weber, change in flux, or change in
Yes,
Weber,
sir.
basically, over time.
Divided by time, yes.
Yes. So I've got -1 because I've got only one loop there. They have to tell you if it's more than one. You can't just see that.
Yes,
Okay,
sir.
I can work this change in flux separately. That's BA cos theta. That's the final one. Minus, you can also put it on top of that thing if you want to.
Yes, sir.
Cos theta. So B is still 1,5 Tesla for both of them. The area will also be, is it 0,012?
Sir?
0,6 times 0,2 is 0,12.
Yes, sir.
I don't know why I put that extra 0 there. 0,12. That's the area. Now, final angle is 60 degrees. Can you see that?
Yes, sir.
Minus initial angle, which was 0 degrees. 1,5 times 0,12 cos 0. I can put that in my calculator. So they factorize, they basically do this. They factorize it out, but you don't have to. You can just type it in like that.
Yes, sir. The answer is negative 0,1692.
That's interesting. Really? Yeah.
Yes, sir.
Fair enough. Okay, so I have negative 0,1692 over the change in time, which is, I don't know, 0,02 seconds. And that gives me 8,646 volts.
Yes, sir, it does.
Okay. So years ago, when batteries weren't developed very well, you had a dynamo. If you ride your bicycle early in the morning and you need a light, you put a dynamo on the wheel. So there's a small little wheel that pushes onto your front wheel, and that wheel turns a copper spool, A copper spool is just one of these loops with a lot of copper wire around it inside a magnetic field, and that's connected by wires to a bulb. So the faster you ride your bike, the brighter the light shines, and the slower you ride your bike, the dimmer the light goes.
Yes, sir.
Because the faster you ride the bike, the faster that dynamo spins inside, and the slower you ride the bike, the slower it spins.
Hmm.
So when you stop at the traffic light, you don't have your light's not on. It's funny. Okay, next one. See what we've got. This is basically what Faraday's law boils down to.
Yes, sir.
And this is okay, let's just do this example together. Copy. This is like a classic example. It's normally not a lot of marks in exam. I don't know if you can see it. It's a bit.
I can see.
You can see it.
Yes.
Consider a flat square coil with 5 turns. Okay, very good. N is 5 in this 5 turns. So there's a coil of 5 loops. The coil is, there's the coil. I'm going to just draw it like that. It's 0.5 meters on both sides. So it's
That means
0.5
this is
by
a square.
0.5. And there's a magnetic field. So B is 0.5 Tesla. So there's a magnetic field of 0.5 Tesla passing through it. The plane of the coil is perpendicular to the magnet. Okay, this is unfair. You understand why people struggle with this? Now they say the plane is perpendicular to the magnet. So what does that mean? Magnetic field. There is the magnetic field.
Yes, sir.
So I'm understanding it as follows. There's my plane. And that plane is perpendicular. You see that?
Yes, sir. Yes,
There's
sir.
my coil. I'm assuming that that's what they mean. So the normal is exactly the same line as the magnetic field. So this position is cos 0 degree. You agree? The
Yes,
angle
sir.
between the coil, the normal and the field is what? 0 degrees.
Hmm.
Okay, good. The field points out of the page, whatever that means. Use Faraday's laws to calculate the induced EMF if the magnetic field is increased uniformly. Now they change the magnetic field. So B initial, the initial magnetic field, B initial is 0.5 Tesla. They
Yes, sir.
changed that to 1 Tesla in 10 seconds. So that is changed to a final B value of 1 Tesla, and that the time it takes is 10 seconds. Determine the direction of the current, induced current. We'll look at this in a second. Well, that's a different question. So let's look at what they've done. They said EMF is minus the amount of spools, change in Tesla, Weber, or change in flux divided by
Yes,
the
sir.
time. I don't know why they didn't put the values in immediately. That is 5 spools. I'm going to work out this separately. I'm going to say change in magnetic flux is B A final cos theta minus B initial A cos theta. The final value is 1 Tesla, and the area was 0.5 squared. Hey?
Yes, sir.
And the angle is going to stay cos 0. We're not changing that spool or that loop.
Yes, sir.
So that's cos 0 degrees, and that's minus 0.5, 0.5 squared cos. So I can't write on that side. Just fix this. Cos 0 degrees. Whatever that is. So I've got 0.5 squared minus. Do you get 8 or 0,1525, 0,125 Weber. No.
Yes, sir.
Okay, then I'm going to put that value in. So it's 0,125 Weber divided by a time of 10 seconds. I get negative 0,0625 volts, which is quite interesting. They're leaving it as negative.
Yes, sir.
That's quite interesting. I always thought you could just leave it as positive volt. Okay. Right. The induced current is anti-clockwise as viewed from the direction of the increased magnetic field. That I'm not sure of. Let's see. They say that the plane of the coil is perpendicular to magnetic field. The field points out of the page. Okay, what they're saying is the following. There is my coil. The field points out of the page. So I'm going to draw this. As the magnetic field comes out. Oh no, the magnetic field points out. You haven't done this. The induced current is anti-clockwise as viewed from the direction of the magnetic field. Okay, anyway, let's see that. So if this points outwards of the page, the magnetic field, then I would say your fingers are coming out. So this is going in. Do you understand what I've just drawn?
Yes, sir.
Okay, but now I'm not getting the answer. The plane, the field is points out of the page. That's correct. In other words, I'm getting my current in this way, which is clockwise. You understand?
Yes, sir.
So what is dumb here is that you could have drawn this little dots other way around. You could have made the dots there as the field coming out of the page. Then this side is going into the page. And
Yes,
then
sir.
current is going in this direction. So they should have given you a drawing. Otherwise you wouldn't know. So I'm taking my right hand, I'm putting my fingers into those dots and I'm putting it around it. So my thumb goes down. So this is how they get it anti-clockwise. Oh, they are right. Why? Because the way to turn the spool is by going over the edge of the spool. So if you go over the edge of the spool, the side of the magnetic field that goes over the edge of the spool, pushing it or turning it, this is over the edge of the spool. So this is the outside of the spool. So it goes inside. So this is the right drawing. So you must visualize yourself, or visualize this is the loop. And there's the two wires coming out of the loop to conduct it. If you want to turn this thing, you must push on the outside of this bar. So there's the side going in. And this is a side going out. If I put my fingers over that, my electrical current will flow in that direction.
Yes,
Again,
sir.
like I said, it's a lot of visualization and it will be one mark, maybe.
It does create mine switch off.
And this basically sums up what you have to do with Faraday's law. Next, you're going to do Lenz's law. Now, Lenz's law is more difficult. It's more visualization. It's got to do with this last part, in which direction it's flowing. But now you're going to change the way your dynamo works. At this moment, the dynamo was a piece of wire, normally copper or something, that you formed into like a square or a circle, and then you spin that inside of a magnetic field. In Lenz's law, we're going to take the magnet and push it through a coil. So you're going to make a coil out of copper like that, a coil, and you're going to push a magnet through it, and it's going to conduct electricity. So you can either put a coil and spin that inside of a magnetic field, or you can take a magnet and push that through a coil. Both of them will conduct electricity.
Yes, sir.
Did you learn anything today?
Yes, sir.
Okay, right. I need to find time to go through that, to go through those memos that you've done. I want to look what you've done. That's not, that might be a stumbling block for you, but you need to send me that paper as well once you can. Okay, so I've got
Yes,
your
may I
memo,
please
but
have
I don't have
your
the
email
physical.
address?
Pardon?
May I have your email address? I'll send you the thing, the question.
I have WhatsApp my email address for
I
you.
don't have a phone anymore, sir.
You don't have a phone anymore,
Yes, sir.
really?
Yes.
Okay. Oh, I can see it's not. So you must just ask ma'am to email your paper as well. She's got my email
Okay.
address. Okay.
Yes. Yes, sir.
Your WhatsApp image is still there. What is it? It's a little.
Sir?
It's SpongeBob
SpongeBob, sir.
with a
Yes,
smoke.
sir.
Huh? What's that, Tatu?
Yeah. It was kind of funny, so I put it there. Yes, sir.
It's kind of funny.
Just SpongeBob, sir.
Yeah. I know.
Yes, sir.
Slightly too
That's
old.
why.
Okay, what you need to do is go through this chapter vigilantly and do the examples. Because this is going to be one of those
Yes.
chapters that you're going to say,
Yes,
okay,
sir.
when the exam comes, I'm going to spend half an hour on it because it's not that difficult.
Okay, sir. I will do.
Electrical Lenz's law we can do next week, and then we're going to start with electrical currents. And that is a lot of marks, and that's much more important.
Yes, sir.
Okay, good. See you again.
Goodbye. Goodbye, sir.